Good morning everyone, and welcome to today's worked exam answer question. Today I am having a look at an AQA A-level thermodynamics question where we will be calculating the Gibbs free energy change for a reaction and using our answer to explain what that means for the feasibility of this reaction at the temperature that we have been given. So there is a few steps that we need to do here, but I do think that 6 marks for this question is quite generous. And I say that because when we're calculating Gibbs free energy changes, we may, as we're being asked to do here, need to work out the entropy change, but sometimes we'll also need to work out the enthalpy change, which we've actually been given. So they've saved us a little bit of work here, but we're still getting quite a decent number of marks for this question. So let's go from the beginning. It says that titanium 4 chloride can be made from titanium 4 oxide as shown in the equation. So we're going to need the equation to work out the entropy change. First thing, we have been given the value for delta H as minus 60 kilojoules per mole. And we're not going to need to do anything with that initially. We're not going to need to convert it in any way because delta G needs to be in kilojoules per mole as well. The minus 60 tells us that it's exothermic, which again, not humongously helpful in its own right, but we've been given it, so we don't have to work it out. The entropy data that we're then shown in the table, we've got an absolute entropy value for all of the reactants and all of the products, and we're going to use those to calculate a value for delta S. And what we can see here is that the units of entropy are in joules per Kelvin per mole. Now, delta H's units, as I've already said, kilojoules per mole, delta G, kilojoules per mole. So once we've worked out our entropy change in joules per Kelvin per mole, we are going to need to convert that into kilojoules per Kelvin per mole. We're asked to use the equation and the data in the table to calculate the Gibbs free energy change for this reaction at 989 degrees Celsius. Now, as the units for entropy are in joules per Kelvin per mole, we're going to need to convert our temperature into Kelvin from degrees. So that's something that we will do as well. And then it says give your answer to the appropriate number of significant figures, which we always should be doing, as I believe I've said before. Whether it tells us to do it to the appropriate number of significant figures or not, we should, because some questions will be expecting that of us, even if they haven't directly stated in the question that they're looking for it. So we'll consider what the appropriate number of significant figures should be once we've got our answer, and then we have to use our answer to explain whether this reaction is feasible. So we need to know what the Gibbs free energy value tells us about whether the reaction is feasible or not. So let's break this down into steps. So as I believe I have said before, I'm a big fan of converting anything that we need to convert sort of at the beginning. So the temperature being in degrees, that is incorrect. It needs to be in Kelvin. So to get it into Kelvin, we're going to add 273 to 989, and that gives me an answer of 1262 Kelvin. So now that's ready to go when I need it. I can't go any further until I've worked out a value for the entropy change, because if I write out the Gibbs free energy equation, which by the way I would always suggest you do because there is usually a mark available for writing out the Gibbs free energy equation, we will see that without the entropy change, we cannot calculate a value for delta G. We've now got our temperature as we need it. We've got delta H been given to us. So the last thing that we need is our delta S. So that would be the next thing that I would do. That is our Gibbs free energy equation. Like I say, get a mark for that. So write that down. If we then want to work out our value for the entropy change, we need to know that the entropy change will be equal to the sum of the entropy values for the products minus the sum of the entropy values for the reactants. And if we have a look at the equation, we may wish to have a little think about the sort of number that we might be expecting to get here. So the products, we've got 2 moles of a gas and we've got 1 mole of a liquid. So in terms of disorder, that's going to be fairly disordered. And comparing that to the reactants, yes, we have 2 moles of a gas, but we then have solids, whereas in the products we've got a liquid. So I think there's going to be an increase in disorder of the system as we move from reactants to products, and therefore that delta S should be positive. Now, we need to figure out what the actual value is, but if at least we've had a look at the state symbols and had a bit of a think about whether that should be positive or negative, it might then help us to just feel confident in our answer here. So when we're summing up the entropy of the products, we need to also remember that all of the values given, the absolute entropy values given in the table, are per mole, whereas we have 2 moles of carbon monoxide being made, we have 2 moles of carbon and 2 moles of chlorine being reacted. So we're going to need to multiply those values up accordingly. So in terms of our products, we are going to have 2 lots of the carbon monoxide, which is 198, and we've then got 1 mole of the titanium chloride, which is 253, and that's going to be for my products. And then I'm going to be taking away from that my reactants, which I'm just going to write underneath to avoid them running out of room. We've got 2 lots of 2 moles, of the chlorine gas, so 2 lots of 223. We've also got 2 lots of the carbon, which is 5.7. I've still run out of room, so I'm going to put it at the front. We've also got 1 mole of the titanium 4 oxide, which is 50.2. So that is going to then give me an entropy change when I put all of that into my calculator of positive 141.4 joules per Kelvin per mole. It's positive, which I was predicting it would be, and of course don't feel you have to put all of that into your calculator all at once. I worked out what the sum of the products was first, which was 649 for this bracket, and then I did the same thing for the reactants, which came to 507.6. Then I did 649 take away 507.6, and that gave me 141.4. Obviously you can put it all into your calculator in one go, but if you're going to do that, I guess make sure you've got all the brackets in the right place that you need. I fear there's more likely to be mistakes that way, but of course it's completely your choice. Now again, we have now got a value for the entropy change, but it's in the wrong units. So as I've said before, with the temperature, always then going to convert my units immediately so that I know that they're ready to sub into the next part of the question. So if I want to get that into kilojoules per Kelvin per mole, I am going to need to divide that by 1,000. And this is one of the mistakes that students make in these questions, is they forget to divide this by 1,000, which means that they're then going to get a very different delta G value, and then a very different kind of explanation as to whether the reaction is feasible or not. Now I've got everything that I need to work out the value for delta G, and then it just becomes a subbing the numbers in to the equation that we've already written down. So delta H minus 60.0, and then we're going to take away from that the temperature, which we've got as 1262 Kelvin, and that is going to be multiplied by delta S, which is 0.1414. And when I put that into my calculator, I get an answer of minus 238.4468 kilojoules per mole. Now, a couple of things. First of all, I'm not going to give it to that many decimal places, but that's the whole display on the calculator. So now we need to consider what the appropriate number of significant figures is going to be. Then we need to know what a negative value for delta G tells us so that we can explain whether this reaction is feasible at this temperature. Just because a reaction is feasible at one temperature won't always mean that it's feasible at another temperature or another temperature, etc. Some reactions are feasible at all temperatures, and this is an example of one of those reactions because it is exothermic and we have an increase in the disorder of the system. So delta G will always show that this reaction is feasible here. For some reactions it will never be feasible. For some reactions it will be feasible below certain temperatures, others it will be feasible above certain temperatures. And we will know whether a reaction is feasible as to whether delta G is positive, 0 or negative. So because it says explain whether the reaction is feasible, we would say this reaction is feasible because delta G is negative. If it's 0 or less than 0, that tells us the reaction is feasible. If delta G is positive, that shows the reaction is not feasible. So that's one of the things that I'm left to do. The other thing that I'm left to do is give my answer to the appropriate number of significant figures. Now, to do that, we always go back and have a look at the number of significant figures that we used for the values in the question. So we were given the value for delta H to 3 significant figures. All of the entropy values in the table for the reactants and products were given to 3 significant figures. The initial temperature was given to 3 significant figures. Therefore, I am going to be giving my answer to 3 significant figures, which is going to turn it into minus 238 kilojoules per mole. And I'm going to show in brackets that I've opted for 3 significant figures. And then I'm going to say that this reaction is feasible at 989 degrees Celsius because delta G is less than 0/negative. And that's all I need to say because it says use your answer to explain whether the reaction is feasible. So we're using the value that we've got for delta G to say, yes, it's feasible because delta G is negative. They may say to kind of do that in relation to the equation itself. So you may not have specific numbers, but you may kind of have to look at the Gibbs free energy equation and go, right, okay, this is exothermic, so that makes delta H negative. There's an increase in the disorder of the system, which makes delta S positive. If I have a negative number and then I'm taking away T delta S, which is going to be positive because delta S is positive, a negative number taking away a positive number will only ever make the answer for delta G more negative than whatever delta H was. And that's the scenario that we have here. But I don't need to explain it in that way because it says use your answer for delta G to explain whether the reaction is feasible. But other questions may say how we would know that this reaction was feasible at all temperatures, and we could say something along the lines of what I've just described. An exothermic reaction means delta H will be negative, T delta S will always be positive regardless of what the value for the temperature is if delta S is positive, and therefore a negative number take away a positive number will always just give us a negative number. Delta G can never be positive in these scenarios. Don't have to do that here. That's all I need to do for this question. I've calculated the Gibbs free energy change, given my answer to the appropriate number of significant figures, and used my answer to explain whether this reaction is feasible. Hopefully that all makes sense, but as always guys, any questions, please just let me know in the comments or send me an email to missgtutoringandresources@outlook.com. I'll be more than happy to assist you. Hope you have a brilliant day, guys.